In this lecture, we will be proving a theorem due to Bloch, which is a prerequisite for proving the Little-Picard's theorem. Bloch's theorem tries to answer the following question. Suppose we have a domain omega, an open connected set omega, which contains the closure of the unit disk D, and consider the family of all those holomorphic functions f defined on omega, which satisfies f of 0 is 0 and f prime of 0 is equal to 1. The question that we would like to answer is, what is the largest disk that can be fitted inside f of D for any f in this family? So notice that the disk we demand should be independent of the function that we pick from the family. We'll begin by proving a special case of the Bloch's theorem. Let me write down the proposition. You can call it a proposition. Let f be a function which is defined on the unit disk such that f of 0 is equal to 0 and f prime of 0 is equal to 1. Suppose we know that absolute value of f of z is always bounded by some number, let's say m, for all z in the unit disk. Suppose we know that f is a bounded function. Then the disk of radius 1 by 6m is contained in f of d. If you notice that the left hand side here, there is no reference to f. Irrespective of what f we pick which satisfies these conditions, the disk of radius 1 by 6m is going to be contained in that. Let's give a proof of this statement. The proof is, it's an elegant proof actually. We know that f of 0 is 0 and f prime of 0 is 1. Consider the power series expansion of f around 0. Of f around 0, and what do we then, f of z will be of the type f of z is equal to z plus higher order terms, maybe a n z to the power n greater than or equal to 2. Notice that f of 0 is equal to 0 tells us that the constant term is 0 and f prime of 0 is equal to 1. Those are the conditions in the hypothesis. Both these conditions tell us, f prime of 0 is equal to 1 tells us that the coefficient of z is equal to 1. And therefore, the absolute value of f of z, if you notice, this is greater than or equal to z minus minus of this, which is absolute value of z minus the absolute value of summation a n z to the power n. Let's focus on the second term. If you look at a n, what is a n? By the Cauchy estimates. By Cauchy estimates, we can say something about a n. Cauchy's estimates tell us that the absolute value of a n is bounded the supremum of z in the boundary of the disk of radius r of f of z by r to the power n. And this we know is bounded by m, right? Because absolute value of f of z is less than or equal to m for all z in d, in particular on the disk, on the circle of radius r, this is also going to be bounded. And this is true for all r less than 1. Remember that f is defined on the unit disk. So in a smaller disk d0r, where r is less than 1, we can talk about the Cauchy estimates, and we have this. By taking the limit as r goes to 1, taking limit as r goes to 1 from values less than from the left, rather, if you take this limit, we have absolute value of mod a n is less than or equal to capital M. So this is what we get to conclude by the Cauchy estimates when we consider the coefficients. And therefore, what we have is the following summation. The absolute value of summation a n z to the power n is less than or equal to m times summation mod z to the power n. Therefore, let's get back to the inequality we are interested in. Mod f of z is greater than or equal to mod z minus this, which tells us that hence mod f of z is greater than or equal to mod z minus m times this is basically mod z square times 1 by 1 minus mod z. So the first observation is that our number m has to be necessarily greater than or equal to 1. Since mod f, if m is less than or equal to 1, in fact if m is less than 1, let's end up with some contradiction, then f will be a map from D to itself with f of 0 is equal to 0 and f prime of 0 is equal to 1, and the Schwarz's lemma tells us that f of z is equal to lambda times z. Now for some z between, so for z such that m is less than mod z less than 1, absolute value of f of z is just going to be equal to absolute value of, this is with mod lambda equal to 1, right? It's a rotation. So here this is just going to be equal to mod z, which is greater than m, which is a contradiction. And therefore we cannot have m to be less than 1. Therefore m has to be greater than or equal to 1. That's an observation that we should keep in mind, because if now we consider 1 by 4m, that's a number which is between 0 and 1, and if you consider for mod z is equal to 1 by 4m, let's see what happens here. What will happen to the right hand side? Mod z minus m mod z square times 1 minus mod z is going to be 1 by 4m minus m by 16m square, which is going to be 1 by 16m by 1 by 4m, 1 minus 1 by 4m. This is precisely what it is going to be. This is going to be 1 by 4m minus 1 by 12m, and again by computing this is going to be 3 minus 1, which is 2 by 12m, which is equal to 1 by 6m. And that's what we get for considering on the circle of radius 1 by 4m. Hence, absolute value of f of z is greater than or equal to 1 by 6m on the circle z, such that mod z is equal to 1 by 4m. Now let's consider the disk of radius 1 by 6m and pick some point there. W be a point in the disk of radius 1 by 6m. Then absolute value of W, which is less than 1 by 6m, this is in particular less than or equal to the absolute value of f of z on the circle of radius 1 by 4m. Now by Roche's theorem, if g of z is identically equal to minus w, then f plus g, which is f of z minus w, and f of z have the same number of zeros counted to multiplicity in the disk of radius 1 by 4m. That is precisely what our Roche's theorem will tell us. And because of that, this tells us that there exists z in D0 1 by 4m such that f of z is equal to w. And since w was picked arbitrarily, it tells us that D0 1 by 6m. Notice that that is what the w was from. That is the disk where our w was from. So D0 1 by 6m is contained in f of the disk of radius 1 by 4, which is in particular contained in f of d. And that is precisely what we had set out to prove. Let us now generalize this result to a bit higher generality by stating and proving the following proposition. We will now not consider functions from a unit disk, rather let's consider f from a disk of radius r around 0, be holomorphic, which is bounded such that bounded by m, let's say, holomorphic function such that, okay, f of 0 is 0, the absolute value of f prime of 0 now is not necessarily equal to 1 but rather some positive number, and such that absolute value of f of z is less than or equal to m for all z in d0 r. Then for this family of functions, we can say that the disk of radius r square mu square by 6m is contained in the image of f, image of d0r under f. We have done the hard work in the previous proposition. The proof here is going to be easy. We are going to reduce this problem to the problem above. And in order to do that, consider the following map. The current map is from d0r to d0, say m, and we will first reduce it to a map from d01 into d0m by composing it with, say, psi 1, which is basically z going to r times z. So consider g of z, which is defined by f composed with psi 1 of z, where psi 1 of z is just r times z. And what happens to the derivative here? F prime at g prime at 0, that's going to be equal to f prime at 0, which is mu, times psi 1 prime at 0, which is r. So this is going to be r mu. So let's now compose it with a psi 2 post composition, which will send it to the following. We would like to have the derivative to be equal to 1. So g psi 2 of z should be equal to z by r times mu. Observe that both r and mu are positive, so this makes sense. So this is just going to go into d0 m by r. This is precisely what we are ending up with a psi 2 here. Now notice that g of 0 is 0, g prime of 0 is equal to 1. You should sit down and check this. It has been arranged so that g prime of 0 is equal to 1, and mod g of z is less than or equal to m by r times mu for z in d0 1. Now we are in the setup as earlier. This tells us that the disk of radius 1 by 6m, which is going to be r mu by 6m, this is going to be contained in G of the unit disk, and that is going to translate into what we want. I'll leave it as an exercise to check that. Then d0 r square mu square by 6m is contained in f of d0 r. Notice that if you translate whatever we have concluded here for g by using the definition of g and f here, then we will be able to conclude what we wanted to conclude in the exercise, and that will complete our result. All right, let's now prove the Bloch's theorem, which is in slightly more generality. The setup is the following. Let me write it down. Let omega be some domain, some open connected set in C which contains the closure of the unit disk. An open connected set in subset of C such that d bar is contained in omega. It's an open set, so let me put the containment to be a strict open set. And suppose f is some function from omega to c such that f of 0 is equal to 0 and f prime of 0 is equal to 1. Then the conclusion tells us that there exists a disk. Let's call that disk something. Let's call the disk D1 contained in D such that f restricted to D1 is injective, and further if you look at f of D1, it contains the disk of radius 1 by 72 in its image, which in particular is contained in f of D. Notice that 1 by 72 is an absolute constant here which doesn't depend on f. So for any function f which is defined in this manner, we will be able to prove that the disk of radius 1 by 72 is sitting inside f of D. Okay, let's now give a proof of Bloch's theorem. The proof is going to be in steps. Let's begin by defining an auxiliary function. Define m of maybe r to be equal to the supremum of absolute value of f prime of z when mod z is equal to r. Basically, it's the supremum of f, absolute value of f prime rather, on the circle of radius r. Then one more function, let's define h of r to be defined as 1 minus r times m of r. So the first observation for you would be that m of r is indeed a continuous function, is continuous on 0 1. I'm only interested in 0 1, so let's focus on 0 1. We'll not bother about what happens outside. On 0 1, m of r is a continuous function. This follows because f prime on the closure of the unit disk, which is compact, is going to be uniformly continuous. Use the uniform continuity of f prime on the closure of the unit disk to prove that m of r is also a continuous function. And if you now look at h is also going to be a continuous function. Hence h. What is h? H is m of r times 1 minus r. H is continuous on 0 1. Let's observe a few things. What is h of 0? H of 0 is 1 times m of 0. M of 0 is mod f prime of 0, which is equal to 1. And h of 1 is just equal to 0. So by continuity, there is a neighborhood of 0 where it is neighborhood of 1 where it is strictly less than 1. Let's pick r naught to be the supremum over all r such that h of r is equal to 1. Can happen that h of r takes 1 multiple times, but we can pick the supremum over all such values r naught, and h of r naught in particular should be equal to 1 by continuity of h. Also, you can check by the intermediate value theorem that h of r will be strictly less than 1 for r greater than r naught. Yeah, that's something which you should sit and check. I told you why it will be the case. Let's now focus on m of r naught. What was m of r naught? Recall that m of r naught is just the supremum of the absolute value of f prime of z, where we range this over the circle of radius r naught. Now, if you look at m of r naught, if you look at the circle of radius r naught, that's a compact set, and f prime being a continuous function attains its maximum at some point. Let's call it z naught. Let z naught be such that mod z naught is equal to r naught and f prime of z naught is equal to m of r naught, because we pick one such point. We also know that h of r naught is equal to 1. Remember that h of r naught is equal to 1, which tells us that 1 minus r naught times the absolute value is equal to 1, which tells us that f prime of z naught, this is equal to 1 by 1 minus r naught. Now consider the following disk. Let rho be equal to half of 1 minus r naught, and consider the disk of radius rho around z naught. Let me draw a picture to capture what we have just done. So this is the unit circle. We have, maybe I should use colors. Red is the circle of radius r naught. There is the point z naught lying here, and then we have the green circle capturing the disk of radius rho around z naught, and the pink is going to be the circle which captures everything, the disk in which everything is sitting. So let's see what happens. Let's pick some point z here. Let z be some point in d z0 rho. Remember that this distance is rho, this distance is r naught, and this distance is going to be equal to r naught plus rho. And you can check that absolute value of z is less than or equal to absolute value of z naught plus absolute value of z minus z naught, which is r naught plus rho, which is r naught plus half of 1 minus r naught, which is equal to half of 1 plus r naught, which is less than 1 because r naught is less than 1. So in particular, 1 plus r naught by 2 is greater than r naught, and this tells us that h of half of 1 plus r naught, this is less than 1. That's precisely what our r naught was picked to be. Why is this the case? This is because half of 1 plus r naught is greater than, so 1 is greater than this, which is greater than r naught. So this is precisely the reason why we have written whatever we have written. And what is this? This is basically telling us that 1 is greater than 1 minus half of 1 plus r naught times m of half of 1 plus r naught. And if we look at this, this tells us that m of half of 1 plus r naught, this is less than 1 by 1 minus r naught times 1 by 2, which is equal to 1 by rho. If you notice, that's precisely how we had picked rho. So rho was not picked arbitrarily if you think about it. So this is true for all points on the circle which is captured by the pink line here, pink curve here. Basically the circle of radius r naught plus rho. And by the maximum modulus principle, we have that absolute value of f of z prime. So this is the supremum, right? By maximum modulus, the absolute value of f prime of z is less than 1 by rho for z in d z0 rho. Let's now consider the following function. Define g of z to be equal to f prime of z minus f prime of z naught. And if we on d z0 rho, then if we look at the absolute value of g of z, that is going to be less than or equal to the absolute value of f prime of z plus the absolute value of f prime of z naught. We know that the absolute value of f prime of z is strictly less than 1 by rho, and we know that the absolute value of f prime of z naught is equal to 1 by 2 rho, and this is just 1 by 2 plus 1, basically 3 by 2 rho. So what we have now is that from the disk of radius rho around g, we have a map rho around z naught, we have a map g into the disk of radius 3 by 2 rho. Let's compose it with two functions which sends it to the unit disk. The map here will be z going to, let's call it psi 2, and the map here psi 1, where psi 1 of z, this is going to be equal to z0 plus rho times z, and psi 2 of z is equal to 2 rho by 3 times z. So if you consider these two maps, we have a composition of holomorphic maps, h of z defined to be psi 2 composed with g composed with psi 1 now is a map from d to d, which maps 0 to 0. And by Schwarz's lemma, we have the absolute value of psi 2 is basically 2 rho by 3 times g of psi 1 of z, which let me compose by the inverse to get the absolute value of psi 1 inverse of z, which let me write it as psi 1 inverse will just be equal to z minus z0 by rho. This is precisely what we have, and therefore the absolute value of g of z is going to be less than or equal to 3 by 2 rho square times the absolute value of z minus z naught. So we are good now because g of z. And one more observation will be that this is going to be a strict inequality because there is a strict inequality here. This strict inequality will tell us that the Schwarz's lemma here cannot be an equality, it has to be a strict inequality. So let's now consider the following disk. Define our D1, which is our goal. The goal was to get hold of a disk D1 where our function f is 1 to 1 and whose image contains the disk of radius 1 by 72. We will come to the 1 by 72 part later. Let's first show that f is indeed injective on the disk, which is given by dz0 rho by 3. And if you observe on this, on d1, let z1 and z2 be 2 points. Then by the fundamental theorem of calculus, f of z2 minus f of z1 is just going to be equal to the integral of f prime of z dz over gamma z1 to z2, the straight line path. The absolute value will be like this. Now that is going to be greater than or equal to the triangle inequality again, which is captured in the following manner: z0 dz absolute value minus the absolute value of the integral of f prime of z0 minus f prime of z dz gamma z1 to z2. This is gamma z1 to z2. The first one is just f prime of z0 times z1 minus z2 minus the absolute value here will be, let me just put it this way and let's focus on that absolute value. Since z1 and z2 are in d1, the distance of the line segment joining z1 to z2 is also in d1, and therefore if you look at f prime of z0 minus the f prime of z, if you look at this absolute value, by Schwarz's lemma we just notice that g of z is basically f prime of z minus f prime of z naught, and that is less than, strictly less than 3 by 2 rho square times the absolute value of z naught minus z, and that is less than rho by 3. So this is going to be strictly less than 1 by 2 rho, but that's precisely equal to the absolute value of f prime at z naught. That's the choice, right? So we have done all the choices so that it fits perfectly when it is needed. So we'll get back to this inequality. Inequality here tells us that this is greater than or equal to the absolute value of integral of f prime of z0 dz, which I have already captured in the form of mod of f prime of z0 times z1 minus z0. And because of the strictness of the inequality, let me replace it by a strict inequality here, minus f prime of z0 times mod of z1 minus z0, which in particular is greater than 0. So what did we start off with? We started off with f of z2 minus z1. We showed that the absolute value has to be greater than 0, which tells us that f is injective on d1, and that is one of the conclusions of Bloch's theorem. We observed that f restricted to D1 is injective. The only thing now left to prove is that this function f indeed has the disk of, it satisfies the condition that the disk of radius 1 by 72 around 0 is sitting inside f of D1. In order to prove that f of D1 contains the disk of radius 71, let's now again define another auxiliary function. This is a new g that I'll use. I don't want to use too many notations. Define g of z to be equal to f of z plus z0 minus f of z0. Where is this defined? This is defined on d0 row by 3. Remember that d1 is dz0 row by 3. This is on d0 row by 3. So this does make sense. And the first observation would be the following. Let's now make a few observations about g. G of 0 is equal to 0. G prime at 0 is the same as f prime at z0, which is equal to 1 by 2 rho. You should go up and check that the z0 was picked very crucially in this manner. And moreover, what do we know about absolute value of g of z for z in d0 row by 3? The first observation would be that z, the curve gamma of z0 to z0 plus z, this is sitting inside d1, right? Then by the fundamental theorem of calculus, f of z plus z0 minus f of z0, this is going to be equal to the integral of f prime of z over this curve. Dz. And if you look at the absolute value, this is bounded here. So we check that the absolute value of f prime of z is bounded by 1 by rho. So this is less than 1 by rho times the absolute value of z, which is now in the disk of radius rho by 3 around 0. So this is in particular less than rho by 3, which is hence less than 1 by 3. So what have we shown here? We just showed that this is absolute value of g of z. So we are now in the setup of our previous problem. Hence, g is now a map from disk to C. G of 0 is equal to 0. G prime of 0 was already computed to be 1 by 2 rho, 1 by 2 times rho, and the absolute value of g of z is less than 1 by 3 for z in D. Let's now go up to the previous theorem. What does the previous theorem tell us? The previous theorem then tells us that d0 r square mu square by 6m, this is contained in d0 r. Yeah, so this is a slight mistake. This is from d0 rho by 3, right? So this tells us that d0, what is r square here? Rho by 3 the whole square, r square mu square. Mu square is 1 by 2 rho the whole square by 6 times 1 by 3. This is precisely what we are interested in. This is contained in g of d0 rho by 3, right? Let's just go back and see what was the conclusion previously made. The conclusion was that d r square mu square by 6m is contained in f of d0 r. Let's now go back to where we are. This is just going to be equal to r square rho square by 3 square into 2 square rho square, that's the numerator, by 6 times 1 by 3, which is 2. This is just going to be equal to 1 by 9 into 8, which is 72. And that's precisely where we are ending up with. So it's actually tailor-made. I should confess that there is some reverse engineering that was involved. This tells us that d0 1 by 72 is contained in g of d0 rho by 3. And now translating it back, this tells us that d0 1 by 72, this is contained in f of d1, which is precisely what we had set out to prove, thereby getting Bloch's theorem.